All right, today we are going to be talking about real zeros of polynomial functions again. And here we go. The rational zeros theorem says, suppose f is a polynomial function of degree n is greater than or equal to 1, of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1. You know this is just a polynomial that has a constant on the end, and then it'll be your first degree with its coefficient, your second degree with its coefficient, all the way up to the nth degree with its coefficient. They just make it look all complicated. Okay, with every coefficient an integer, and a sub naught obviously cannot be 0. If x equals p over q is a rational zero of f, where p and q have no common integer factors other than 1, then p is an integer factor of the constant coefficient a sub naught, and q is an integer factor of the leading coefficient a sub n. What does that mean? It means, let's say that I just make a really simple polynomial, like 3x cubed minus 2x squared plus 4x minus 4. Okay. If this function, okay, I have no idea what this function is, I'm just completely making it up, but this tells me that it could cross at most 3 times. Okay, so I don't know if that's the graph. I could use a graphing calculator, I don't know, but that's not the point. I'm just making this up. It could cross as many as 3 times. However, I don't know if these intercepts are rational or irrational. What rational means is that it crosses at some point that even if it's not a fraction, it can be written as a fraction. Like if it was at 0.5, I could write that as a fraction, 1/2. 0.25, that can be 1/4, okay? As long as you can write it as a fraction, it's a rational zero. But let's say that this thing's crossing right here at 3 minus the square root of 2. That's not rational. Anything with a radical in it that's not a perfect square is going to be irrational, meaning if you typed this in a calculator, got a decimal equivalent, and tried to write it as a fraction, it can't, because it's irrational. That number goes on forever and ever and ever, but there's no pattern to it. It doesn't repeat. Okay, so it's irrational. So it doesn't mean that it doesn't cross somewhere. It doesn't mean that it's not real. It just means that it's not rational. So what they're saying is, if you are at a rational zero, not an irrational one, this theorem doesn't count for them. But if you're trying to look for rational zeros and you find one, then guaranteed, whatever that number is, okay, it can be written as some factor of p over some factor of q. So for example, if I was just looking for the rational ones, again, this doesn't help me find irrational ones, but if I'm just looking for the rational ones, I could say, well, it says that if it's a rational zero, then p has to be a factor of the a sub naught, of your constant. So this would be my p values come from all the factors of 4. And my q values are going to come from the coefficient a sub n. So what you do is you get all the factors of p. So all the factors of 4. 1, 4, 2, and 2. Okay? And you get all the factors of q. All the factors of 3 would be just 1 and 3. And then you make your list of possible p over q's. Well, my first p is 1. And I'm going to pair that up with this 1 and this 3. So I could make 1 over 1 and I could make 1 over 3. That one is done. I've got all the possibilities out of it. Then I move to my next p, which is a 4. So I could pair it up with the 1 and the 3. So I could write 4 over 1 or 4 over 3. And then my final one is a 2. And I can pair them up with 1 and 3, which would give me 2 over 1 and 2 over 3. So my final PQ list is plus or minus 1, plus or minus 1/3, plus or minus 4, plus or minus 4/3, plus or minus 2, and plus or minus 2/3. If this thing crosses at a rational number, it has to be one of these. Has to be. This theorem guarantees it. So you're saying, well, great, what good does this do me? Well, in the olden days, before we had graphing calculators, this theorem was huge. It literally saved people hundreds of hours looking in, not, I'm kidding, I'm exaggerating, looking for zeros all over the place. I mean, if before we just said solve this, they're asking you to find the x-intercepts. They're asking you to find where it crosses the x-axis. Well, it could cross anywhere, so we thought, until someone sat down and realized that every time they solved it and actually found these zeros, the rational ones anyway, they were always a combination of this p over q, which is pretty fascinating. So once you figured that out, if you were then trying to just randomly find the zeros of a function, you didn't at least have an infinitely number of possibilities. Now I can limit it to 2, 4, 6, 8, 10, 12 possibilities. Instead of having to check every number in the universe, now we only have to check 12 numbers. So in its day, it was a huge theorem. Of course, now with graphing calculators, you just type it in and calculate the zero and be done with it. But again, you don't get to do that. All right, so to use the rational zeros theorem to solve polynomial equations, you're going to find your PQ list. And again, in the olden days, understand, you would just have to use this list and you would just have to start doing synthetic division or long division and see which ones worked. If you got a 0, then it was a factor because there's no remainder. If you didn't get 0, then you had a remainder, which means it wasn't a factor. You'd literally just have to do 12 math problems to figure out if this thing crossed there at all. I mean, no, there's no guarantees it crosses 3 times. This thing could only cross once. Maybe it does something like this, and so maybe that's an irrational number and it won't cross at any of these numbers. But if it does cross at a rational number, I promise you it's in this list. Okay? So you make that PQ list. Again, in the olden days, you would have had to just suck it up and do this math problem 12 times. Today, we're going to cheat a little bit. We're going to use a combination of the theorem and a little bit of technology, graphing calculator. So we're going to make the PQ list. Then we're going to graph the function on the graphing calculator. Okay, I want you to sketch it on your paper, if you were doing it on paper. Then use your graph to find one or more zero from your PQ list. Again, it's kind of cheating. It's even taking us further. First of all, we're going to by hand. We're going to do in the olden days, we're going to limit the endless possibilities down to our PQ list. And then we're going to use today's technology. We're going to use the graphing calculator, and we're going to see if we can see any of these on the graphing calculator. If we see them, then we're going to use synthetic division to depress the polynomial. And I don't mean make it sad in therapy. I mean we're going to divide it down. We're going to divide by one of the factors, which will drop it. Remember how we talked about every time we, like if our function was a 5th degree and we divided, it would drop it down to a 4th degree? That's what it means. It's going to drop the degree down. We have to find enough zeros, okay, to divide by until our polynomial is a 2nd degree. Once it's a 2nd degree, then we can use our quadratic techniques. We can either use factoring or quadratic formula to find the remaining zeros. Okay? So here we go. It says use the rational zeros theorem to write a list of all potential rational zeros. Then determine which ones, if any, are zeros. So just remember, if you ever screw up, where does the P's come from and where do the Q's come from? It's not alphabetical. That's where people screw up. They think that, well, this is the beginning, so that's P, this is the end, it's Q. Now it's backwards. Your P's come from the constant, your Q's come from factors of the leading coefficient. So to find all my factors of P, I want all the factors of 8, which would be 1, 8, 2, 4, and that's it. And then to get my Q list, I want all of the factors of 2, which, thank goodness, there's only 2 of them, 1 and 2. Okay, so then we're going to make our PQ list, and we literally just start pairing these guys up. Okay, I compare, let me find a new color. I compare, if I start with the 1, I compare it with both of these. So 1 over 1, 1 over 2, and I'll add my commas and pluses or minus later. Okay, and then I'm going to move on to 8, and I can write that 8 over 1, pair it up, and 8 over 2. And then I go to my next 1, which is 2, and I pair it with 1 and 2, so 2 over 1, 2 over 2. And then I go to my last one, and I pair it up with 1 and 2, and I have 4 over 1 and 4 over 2. So let's simplify these and get rid of any repeaters if we have them. 1 divided by 1 is 1, and it's always going to be plus or minus. So we have plus or minus 1, plus or minus 1/2. 8 divided by 1 is 8, so we have plus or minus 8. 8 divided by 2 is 4, so we have plus or minus 4. 2 divided by 1 is 2, so we have plus or minus 2. 2 divided by 2 is 1, which we already have, so I don't need it again. 4 divided by 1 is 4, which we already have, so I don't need it again. And 4 divided by 2 is 2, which I already have, I don't need it again. Okay, so those are all my possibilities. If this thing, and this thing could cross 4 times or 2 times, or no times. Remember, your degree tells you how many times it could cross, or less than that by 2. So this thing could cross 4 times, 1, 2, 3, 4. It could just cross twice, or it couldn't cross at all. Okay? So, I don't know if any of these, if it's going to cross at any of these or not. But if it does, if it has any rational zeros, if any of these points are rational, it's in this list. So there's no need for me to see, does this thing cross at positive 10? Or is there a 0 at 12? Or is there anything, is it going to cross the x-axis at negative 5? Okay, if it's not in the list, it ain't going to cross there. Rationally, anyway. So now what we're going to do, again, in the olden days, you would just start dividing by positive 1. If it worked, great. If it didn't, move on to negative 1. If that one didn't work, move on to you just go through the list until you tried them all. We're going to cheat a little bit, okay? We're going to use a little bit of today's technology. So I'm going to go to my graphing calculator, and I type it in, and this is what I got, okay? Now, I'm looking at my list, and I'm looking at my zeros. I got a 0 there, I've got a 0 there, I've got one right there, and I've got one right there. I'm going for this big one because I can tell perfectly it crosses at 4, and 4 is in my list, okay? So I got me one. And if you even wanted to check, you could. I even did calculate 0, and it does cross at 4, 0. So that means I found one rational 0. Okay? So I'm going to divide by 4. Okay? And I'm going to do synthetic. 0 is 4, so I'm not changing the sign because this is a 0. Alright? My coefficients are 2, negative 7, negative 8, positive 14, and positive 8. Alright, 2 comes out, brings back 8, negative 7 eats 8, positive 1 comes out, 1 times 4 is 4, brings back positive 4, negative 8 eats positive 4, comes out negative 4, negative 4 times positive 4 is negative 16, positive 14 eats negative 16, negative 2 comes out, negative 2 times 4 is negative 8, negative 8 eats, positive 8 eats negative 8 and comes out 0, which that better have happened or my graph is lying to me. Okay, it has to have a remainder of 0. Now you have depressed your polynomial. This was a 4th degree. Now it is a 3rd degree. So 2x cubed plus 1x squared minus 4x minus 2. Okay? I still can't, so I've got 1. I'm looking for 4 tops, right? There's 4 answers. There has to be 4 answers. I just don't know how many of them are rational. So far my zeros are positive 4. Now I've got to look for another one. Well, this one I'm not real sure about. It doesn't look perfectly halfway in between. Neither does this one. But that one, because I noticed this fraction right here. I mean, I looked at 2. They didn't cross at positive 2 or negative 2. Not exactly. It didn't cross at positive 1 or negative 1. It didn't cross at 8 and negative 8. It didn't cross at 2 and it didn't cross at negative 4. So I'm going, that one looks almost perfectly in between. So I'm going to think it's 1/2. And again, I'm cheating a little bit because I can zoom in and see or calculate that 0. And sure enough, it's crossing at negative 0.5. Now, you guys don't like fractions, but I promise when this happens, it always, the only way you're going to get a remainder of 0 is if that denominator constantly cancels out. So watch how neat this is. I'm going to put negative 1/2 in the hole. And I'm going to use my depressed polynomial. 2, positive 1, negative 4, negative 2. Okay? 2 comes out. And if you do 2 times negative 1/2, those 2 cancel, and you bring back negative 1. Positive 1 eats negative 1, and 0 comes out. 0 goes back, multiplies by negative 1/2, and brings nothing back. Church. Negative 4 eats 0 and comes out negative 4. Negative 4 goes to the store and multiplies, and if I take negative 4 times negative 1/2, that's positive 4 divided by 2 is 2. She brings 2 back. Negative 2 eats positive 2, and no remainder. Again, that has to be true, or my calculator's lying and it's not really crossing at negative 1/2. So now we've depressed it down from a 4th degree to a 3rd degree. Now my 3rd degree has been depressed down to a 2nd degree. So there's my 2nd degree, my 1st degree, and my constant, which means my quadratic that I have left is 2x squared minus 4. This problem, okay, is now a quadratic, which I can solve using, I can find these other 2 solutions, these ones that I'm not sure about, here and here. Okay, so I'm sorry, we found 4, we found negative 1/2. And I can see the other 2, they're real, but they're not in this list. I mean, I could try, I could keep, I mean, look, I calculated them on the calculator, and you see these long decimals I get? Those are not, they're not in that list, which tells me that they're not rational. So you can use, to find them, you use our quadratic techniques to solve a quadratic equation. So you set this to 0 and solve it. You can factor, you could do quadratic formula, but this one I'm just going to use the square root property. When you don't have a 1st degree x, just isolate what's being squared and kill it. Square root it. That'll get rid of it. So to isolate it first, I'm going to add 4. That gives me, wait a minute, hold on. Oh yeah, plus 4, sorry. 2x squared equals 4. Alright, then I'm going to divide by 2. Divide by 2. I get x squared equals 2. Then I'm going to square root, and I get x equals plus or minus the square root of 2. And I promise you, type in a positive square root of 2 on your calculator, and it's going to give you 1.41422136. Type in negative square root of 2, and it's going to give you negative 1.414221 whatever. Okay? Alright, so it says, write a list of all potential rational zeros and determine which ones, if any, are zeros. The only ones in my list that are zeros are 4 and negative 1/2. If it asked you to find them all, okay, I just kind of did it all in one problem. If it asked you to not only find the rational ones, but then to find all of them, I mean, to answer this question alone, that would be my answer. To find all of the zeros, irrational and rational, then your list would include 4, negative 1/2, positive square root of 2, and negative square root of 2. Notice these are not in the list because they're not rational. Okay? Alright, so you hit pause and try this one. See how well you do. Come back when you're ready. Alright, this one just says to write a list of all potential rational zeros. You don't actually have to see which ones of them are. You're just making the list. Well, again, don't go alphabetical. It's P at the end, Q at the front. So for my P, I need all my factors of 10, which are 1, 2, 5, and 10. I mean, how you find them? You know, you're just finding all the numbers that go into 10 evenly, and then their product or their quotient. Your Q is my 5. The only factors of 5 are 1 and 5. So to make your list, you start with your first P, and you line them up with both of your Q's. So my P over Q list is going to be 1 over 1, 1 over 5. Then you move on to the next one. I'm going to line up my 2 with my 1 and my 5, so 2 over 1, 2 over 5. I'm going to line up my 5 with 1 and 5, 5 over 1, 5 over 5. And then I'm going to line up my 10 with 1 and 5, so 10 over 1, 10 over 5. Let's clean it up and get rid of any repeaters. My P over Q list, 1 divided by 1 is plus or minus 1. 1 divided by 5 is plus or minus 1/5. 2 divided by 1 is plus or minus 2. 2 divided by 5 is plus or minus 2/5. Plus or minus 5 divided by 1 is plus or minus 5. 5 divided by 5 is 1, I already have it. 10 divided by 1 is plus or minus 10. 10 divided by 5 is 2, I already have it. So there's my PQ list. Okay? Alright. And try this one. Now this one says find all of the rational zeros. Hit pause, come back when you're ready. And did you find there were none? Okay, I can make my PQ list. My P is going to come from the 8s. Remember, P's at the end, Q's at the front. Q is 1. So my factors of 8 are 1, 2, 4, and 8. My factors of Q are 1, so that makes it real easy. So my PQ list is 8 over 1, 1 over 1, 2 over 1, 4 over 1. Oh, I already said 8. Oh yeah, and 8 over 1, but I already got 8. Sorry, I wrote that 8. Alright, so if we clean that up, my P over Q list is plus or minus 8, plus or minus 1, plus or minus 2, plus or minus 4. Now, again, normally in the olden days, I would try starting to divide. I would put 1 in the whole, and I would have my 4th degree, my 3rd degree, my 2nd degree, my 1st degree, my constant. And 1 would come out, bring back 1, come out 3, bring back 3, bring out 5, bring back 5, come out 1, bring back 1, come out. I got a remainder. And I promise, if you checked all 2, 4, 6, 8 of those, you're always going to get a remainder. In other words, there are no rational zeros. Okay? If I tried every single one of those, I would get a remainder every time. Okay? Again, we cheat a little bit. I went and looked at the calculator, and I'm like, well, see again, at 4th degree, I was expecting it to either cross 4 times or 2 times or no times. This one crossed twice. And if I look over here and I calculated, I looked at the 0 first before cheating, and these are all whole numbers. That clearly is not on a whole number, neither is that, which means they're real, but if it ain't in the list, it's not rational. So when I calculated them, sure enough, they're not rational. They're those big long decimals, which go on forever and ever, and never repeat. Alright, so explain the rational zeros theorem. If a function has, that's a big if, has rational zeros, they will be located at some P over Q, where P is a factor of C, the constant, and Q is a factor of the leading coefficient. Okay? Alright, it says next, use the graph to guess possible linear factors of f of x. Then completely factor f of x with the aid of synthetic division. So again, I got a little bit ahead of myself on the first one. If I look at this graph, again, if I just looked at the function, I'm expecting 3 or 1 intersection points. When I saw the graph, there's 3. Okay, I can see this one for sure, I know, is at -3. This one, I'm for sure, is at +1. This one, I'm not so sure of. Okay, I can make my P over Q list. The factors of 51 are only 1 and 51. Factors of 5 are only 1 and 5. It ain't there. Okay, so, See, 1 and negative 3. Anyway, my graph there shows me that I know for sure these two are rational because they're whole numbers. So if I have to find them all, the only one I'm not sure about is this one. And since, I could type it in the calculator and get it that way. But watch, if I could just even use one of these, I can divide this is a third degree. If I divide by this guy, that'll drop him to a second degree. And then I could use quadratic techniques to find the other two, except for I already know one of the other twos. I could actually just divide the second degree by that, and that would drop it to a first degree, which would tell me what this is. So let's do that. All right, I'm going to use this one. You know what? I'm actually going to use my PQ list. Okay, P is going to come from factors of 51, which are 1, 51, 2 doesn't work, 3 goes in there, 1, 17 times, and I think that's it. My Q is factors of 5, 1 and 5. So my possibilities are 1 over 1, 1 over 5. 51 over 1, 51 over 5. 3 over 1, 3 over 5. 17 over 1, 17 over 5. So that's plus or minus 1, plus or minus 1/5, plus or minus 51, plus or minus 51/5, which is 10 something, plus or minus 3, plus or minus 3/5, plus or minus 17, and plus or minus 17/5, which is 3 something. Well, again, in my list, I see the negative 3, gotcha, and I see the positive 1, gotcha. This one, 1/5 is 0.2 something. That would be over here, so it's not that. It's not 5. They're 51, clearly. 51 divided by 5 would be 10 something. All three are right here. There's no way anything else is happening that far out. Okay, what is that? 3/5? 3/5 is 0.6 something. Again, that would have to be over here. I can't read my writing. What was after 3/5? 17? There's nothing out there. Right? And 17/5, that'd be 3 something. 1, 2, there's my, that could be, it could be the 17/5. I didn't even think of that. It could be that one. Oops. Sorry, jumped ahead. All right, so at any rate, we're going to use our 2 for sure ones and get this down to either a second or a first degree. So if I put negative 3 in the hole, my coefficients are third degree is 5, second degree is negative 7, first degree is negative 49, and my constant is 51. Okay, 5 comes out, brings back negative 15, comes out negative 22, brings back positive 66. Give me just a second. Sorry, had a phone call. Okay, so we have negative 49 plus 66. Let me try that again. Negative 49 plus 66. I get 17 comes out. 17 times negative 3 is negative 51. That gives me 0 for a remainder, which it better be or my calculator's lying to me. So now we've depressed this down to, sorry, I don't know why my color changed. We've depressed this down to a second degree. So now I have 5x squared minus 22x plus 17. If I wanted to now, I could do quadratic formula to that. I could factor that. I could complete the square with that. It's now a second degree equation, which we have tools to solve. Okay, but if I'm trying to find all three and I know this one, I can put that one in the hole now and use my second degree coefficients, 5, negative 22, positive 17, and I can do synthetic division here. So 5 would come out, brings back 5, negative 22 plus 5 is negative 17, times 1 is negative 17, remainder 0. So now I've got from a second degree down to a first degree. So now what I have left is 5x minus 17. So again, at this point, it is going to be this one. All right, at this point, if I take a first degree, you know how to solve first degrees and second degrees. We know how. First degrees, you just you both set them to 0 and solve. But a first degree, you just get x alone. Plus 17, 5x equals 17, divide by 5, divide by 5, x equals 17 fifths. There it is. There's the third one. I wasn't really expecting that, actually. Okay, but again, if you would have backed up here, once you get down to second degree, we have tools. First degrees you've known how to solve since Algebra 1. Second degrees, you know how to solve by using quadratic formula, factoring, any of those techniques. If you would have done quadratic formula up here, you would have gotten the 1 and the 17 fifths. Okay? All right. You try this one. Come back when you're ready. All right, and hopefully you got 3. If I'm looking at this graph, I can tell for sure, I mean, I could make my list, but again, when they give me a graph, why am I going back 100 years and doing the list? They're already letting me cheat. So for sure it crosses at -2. I don't know about that one, and for sure it crosses at +6. So if this is a third degree, I can divide by one of these, or again, by dividing by one of these will drop it to a second degree, which then I could use quadratic formula and I would get the other 2. But if I did this one and dropped it down to a second, and then I did this one and dropped it down to a first, then solve the first degree, then I can figure out that one in the middle. Okay? So I'm going to do -2 first. So I put -2 in the hole. My coefficients are 7, -39, -40, +132. All right, 7 comes out. 7 comes out, brings back, sorry, this pen, if I hit that little button. 7 comes out, multiplies by -2, -14. -39 eats -14 and comes out -53. -53 times -2 is 106. Brings back -40 eats 106 and comes out 66. 66 times -2 is -132. +132 eats -132 and zeros my remainder, which it better have been, or my graph is lying to me. So now we are down to a second degree equation, which at this point I could use quadratic formula or try and factor, but that does not look fun. So since I know this other one, 6, works for sure, I'm going to put 6 in the hole and use my second degree coefficients. So 7, -53, +66. Okay, 7 comes out, multiplies by 6, brings back 42, -53 eats 42, comes out -11, times 6 is -66, which gives me a remainder of 0. That drops me down to a first degree equation, and to solve a first degree equation you simply get x, set it to 0 and get x alone. So add 11, I get 7x. Oh, actually we didn't find zeros, they left them as factors. Oops. Okay, let me finish. So 7x equals 11, divide by 7, I get x equals 11 sevenths. Okay, so now let me show you how they end up with this answer. Okay, so what I have figured out is that x equals -2, that x equals +6, and that x equals 11 sevenths, correct? What they want is, they didn't ask for the zeros. They said completely factor it. Well, what they're saying is turn your zeros now into factors. Remember when we had the zeros and we backed up to factors and we multiplied them together to get the function back? That's the same thing we're doing here. To write it as a factor, we want 0 back on this side. So add 2. So I have x plus 2 equals 0. So one of my factors in my function is x plus 2. Okay, the same thing with the 6. To move it over, -6, I get x minus 6 equals 0. So my next factor is x minus 6. Now this one, you could just subtract 11 sevenths, but again, notice how they're writing it. And it's just because they killed the fraction. They said times 7 gives me 7x equals 11. And then they said minus 11 minus 11, 7x minus 11 equals 0. So there's my third factor, 7x minus 11. Okay? All right, so it says explain the rational zeros theorem. We just did that. Sorry. I don't know why I put that slide in. Okay, now the last thing we're going to do is write polynomial equations given the zeros and its leading coefficient. All we have done before is they've given us the zeros. Now they're including, they want us, we just kind of ignored the fact that there could be some sort of a leading coefficient on the thing. And now again, as we go through, we're getting more and more detailed about our functions that we're learning about, okay? So now we're worried about the leading coefficient. Well, they're either going to give it to you or they're not. Okay, if they give it to you, you write the given zeros as factors, just like we did before. Then you write the equation. Your function will be the leading coefficient they give you times your factor 1 times your factor 2, blah, dot, dot, simplify, and you got your equation. Let's look at those first, okay? So it says find the polynomial function with the given leading coefficient, degree, and zeros. So the leading coefficient is 2, degree is 3, and -1, 3, and -5 are 0. -5 are zeros. So the first thing is they're telling me x equals -1, x equals 3, x equals -5. Remember, I want those as factors. So plus 1 gives me x plus 1 equals 0. -3, x minus 3 equals 0. Plus 5, x plus 5 equals 0. Okay, so now let's put it together. My function is going to be my leading coefficient, which they told me was 2, times all my factors, x plus 1, x minus 3, x plus 5. Sorry, writing. There's my function. Except for they want it written in standard form, which just means multiply it all out, 2 at a time. If I distribute the 2, I get 2x plus 2. Drop the next one, x minus 3. 2x times x is 2x squared. 2x times -3 is -6x. Positive 2 times x is positive 2x. Positive 2 times -3 is -6. Combine like terms. 2x squared minus 4x minus 6. All right, and then don't forget my third one. The x plus 5 still needs to come down. And we multiply that out. 2x squared times x is 2x cubed. 2x squared times 5 is 10x squared. -4x times x is -4x squared. -4x times 5 is -20x. -6 times x is -6x. -6 times positive 5 is -30. And if we round up all of our like terms, I have no other x cubes. I have a positive 10x squared and -4x squared, which gives me a positive 6x squared. I have a -20x and a -6x, which gives me a -26x, and no other constants, so drop it. And that, my friends, is my function that has those zeros, degree 3, sure enough, and a leading coefficient of 2. Good job. All right, now the other one. It says using only algebraic methods, find the cubic function with a given table of values. In other words, they don't want us to cheat and plot those points and do a cubic regression. Okay, we have a couple of things. Do you see where I have the zeros? They're not telling me in words, but my table is telling me that x equals -2, that x equals 1, and that x equals 5, because there's zeros in the y column, okay? Why did they put an extra point in there? That's to help me get my leading coefficient, okay? So the first thing we're going to do is says write the given zeros as factors, okay? So would you agree that, can I skip this? Add 2, that's going to give me x plus 2. -1 is going to give me x minus 1. -5 is going to give me x minus 5. Okay. So we have that, and then it says we're going to plug in the ordered pair that is not a zero of the function into everywhere. Okay, see how they're giving me an x and a y ordered pair? This -1 is my x, this 24 is my y. So everywhere I see a y, I'm going to put, and I have to put my leading coefficient. I don't know it, but that's where it's going to go. Okay, so when I do this second step here, I'm writing my y equals, no, I'm sorry, my y is 24, so I'm replacing that with 24, equals my a, I didn't put here because I don't know what it is, but that's my leading coefficient. And everywhere I see an x, I'm going to put -1. So I have -1 plus 2, -1 minus 1, -1 minus 5. Okay, and I'm going to solve this thing for the leading coefficient, for a. Okay, so I'm going to have 24 equals a, -1 plus 2 is 1, -1 minus 1 is -2, -1 minus 5 is -6. That is going to give me 1 times -2 is -2 times -6 is 12. That is going to give me 12a, divide by 12, and I get a equals 2. So now I can write my whole function all over again, but I can put my a right here and simplify it out. Okay, so I have y equals, I'm tired of green, y equals 2 times x plus 2 times x minus 1 times x minus 5. But again, we have to simplify that. So if I distribute the 2, I'm going to have 2x plus 4, drop the x minus 1. That's going to give me 2x squared minus 2x plus 4x minus 4, which simplifies to 2x squared plus 2x minus 4. And then I need to multiply that by x minus 5, which gives me 2x cubed minus 10x squared plus 2x squared minus 10x minus 4x plus 20. I'm just distributing. Yes. Combining like terms, no other cubes. Negative 10x squared, positive 2x squared is negative 8x squared. Negative 10x, negative 4x is negative 14x, and positive 20 comes down. And there, my friends, is a function that would match that table of data. Okay? Alright, so you try this one. It's like the first one we did. Push pause, come back when you're ready. Alright, so it said, find the polynomial function with a leading coefficient of -7, degree 3, and these is your zeros. X equals -4, x equals 4, x equals 2. Write them as factors, add 4, that's x plus 4. Minus 4, that's x minus 4. Minus 2, that's x minus 2. And then we multiply it all together. Multiply here, I get -7x minus 28. Bring down the next one, x minus 4. -7x times x is -7x squared. -7x times -4 is positive 28x. -28 times x is -28x. -28 times -4 is positive 112. Clean it up, combine like terms. The 28x's actually cancel, and that gives me -7x squared plus 112 that I still have to multiply by x minus 2. Oh my gosh, Tamsin, look at what, sorry. If they wanted this in standard form, I'll just keep going now. That's going to be -7x cubed, positive 14x squared, plus 112x minus 224. that would be my function in standard form. Sorry, your insightful teacher didn't even look at the answers. They left it in polynomial form. So -7, just in other words what I wrote here, they stopped and they were done. Alright. Okay, this one, stop and do yourself. Remember, you're going to have to use this ordered pair to figure out what the leading coefficient is. Okay? Come back when you're ready. Alright, and hopefully you didn't do all the work like I did last time. We only have to get it in factored form, not in standard form. So this table tells me that x equals -7, x equals -6, and x equals 1. So as factors in my function, I'm going to have some leading coefficient times x plus 7 times x plus 6 times x minus 1. And again, if I'm losing you, add 7, there's my x plus 7, add 6, there's my x plus 6, minus 1, there's my x minus 1. Now we're going to use this ordered pair over here, plug this in for x and this in for y to figure out what my leading coefficient is. So I'm going to change y to -1056 equals a, 5 plus 7, 5 plus 6, 5 minus 1. That's -1056 equals a times 12 times 11 times 4. That's -1056 equals 12 times 11 times 4 is 528a. To get a alone, divide by 528, and a equals -2. So if I plug in -2 there, my function is -2, x plus 7, x plus 6, x minus 1. Yeah. And the order you put those in actually doesn't actually matter. Alright, so it says, how can the graph of a polynomial function help in finding all the zeros of the function? Because if you divide by the zeros you can see, by zeros you can see on the graph, you will depress your polynomial to either first or second degree, which can then be solved algebraically. Okay. Alright, upper and lower bound tests for real zeros. It says let f be a polynomial function of degree n greater than 1 with a positive leading coefficient. Suppose f of x is divided by x minus k using synthetic division. If k is greater than or equal to 0 and every number in the last line is non-negative, positive or 0, okay, then k is an upper bound for real zeros of f. So two things has to happen. This value of k has to be positive. In other words, this has to look minus, okay? Yeah, if k is, yeah, okay? Then if you do synthetic division, and every number on the last line, meaning on your equation line, is positive, including the remainder, then you have found an upper bound. If k is negative, and the numbers in the last line alternate between non-negative and negative in any order, then k is a lower bound. Well, what does this mean? Well, sometimes, when we graph functions on a calculator, we see things like, like this. Well, you can only see so much in a calculator window. How do I know that this function doesn't turn around and come back and cross some more times? In other words, how do I know there's not more zeros out there that I can't see because my window's not big enough? Well, that's why we have the upper and lower bound test. Let's say that you're not necessarily finding a 0, but let's say that I picked a number right here on the graph. Let's say it was 9. If I pick 9, okay, and k is my 9, that's greater than 0, okay, then it's going to be an upper bound if and only if, when I divide by it, when I put 9 in the hole and I put my coefficients, if every number that comes out on this last line is positive, then what that guarantees is, I don't know what this graph does, but I promise you it's not going to come back and cross the x-axis at any point after 9. Okay, if I wanted to like test, let's say that this was -10. If I wanted to make sure that this thing didn't come back out and snake back around and hit the x-axis anymore down here, okay, k would be negative, it's less than 0. Okay, if I put -10 in the hole, and these alternated, positive, negative, positive, negative, positive, negative, all the way down, even including the remainder, then you found a lower bound. You're not finding a 0. It's not saying that the function crosses there. It's just telling you whether it will or will not possibly cross any more after that. Okay? So it says use synthetic division to prove that the number k is an upper bound for the real zeros of the function f. So you just divide by it synthetically. My 4th degree coefficient, 3rd degree coefficient, 2nd degree coefficient, 1st degree coefficient, constant. Okay, my zombie apocalypse. Positive 1 comes out, goes to the store, gets 2, multiplies, brings back positive 2. Negative 1 eats positive 2. Positive 1 comes out, goes to the store, multiplies by 2, brings back positive 2. Positive 1 eats positive 2. Positive 3 comes out. Positive 3 goes to the store, gets a 2, brings back positive 6. Positive 1 eats positive 6, comes out positive 7. Positive 7 multiplies by 2, brings back positive 14. Negative 12 eats positive 14 and comes out a positive 2. So let me ask you this. Is 2 a 0? No. Why? Because I got a remainder. But is it an upper bound? Meaning, whatever this thing does, it won't cross the x-axis. It's going to do all its wiggling and jiggling over here, but it's not going to cross the x-axis after 2. It won't cross anywhere upper of 2. It is an upper bound because every sign on the last line came out positive. Positive, 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 positive. I don't care what the numbers are. They all came out positive, which says it's an upper bound. You can even get zeros there, but they have to be positive or 0. Okay? Alright, so if I do this one, it says prove that the number k is a lower bound. To prove that k is a lower bound, my last line has to alternate signs. So you put -3 in the hole. My 3rd degree coefficient, 2nd degree coefficient, 1st degree coefficient, and constant. Okay, positive 1 comes out, goes to the store, brings back -3, positive 2 eats -3, negative 1 comes out, times -3 is positive 3. Positive 2 eats positive 3, comes out positive 5, multiplies by -3, brings back -15. Positive 5 eats -15, comes out -10. That's my remainder. So is -3 a 0? No, because I got a remainder. But is -3 a lower bound? Only if you alternate signs on the last line. Positive, negative, positive, negative. They alternated, so yes, it is a lower bound. Okay? Alright, you try this one. Come back when you're ready. And hopefully you got... Don't freeze on me now. Yes. All right. If I put 2, they're trying to test to see if it's an upper bound. That has to be positive. If they said test k is 2 as a lower bound, that's silly. It's not even meeting the criteria. K has to be positive to be an upper bound. It has to be negative to be a lower bound. All right. My 4th degree, my 3rd degree, my 2nd degree, my 1st degree, and my constant. Okay. 5 comes out. Multiplies by 2, brings back 10. 4 eats 10, comes out 14. 14 multiplies by 2, brings back 28. -5 eats 28, comes out 23. 23 multiplies, brings back 46. 2 eats 46, comes back 48. 48 goes to the store, multiplies by 2, brings back 96. 3 eats 96 and comes out 99. which is my remainder. Okay, so 2 is not a 0, but is it an upper bound? Well, upper means that all of the signs are positive. Positive, 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 positive. It is an upper bound. Okay? Alright, so oh, that was the only one. Alright, so how do you determine the upper and lower bounds of real zeros? Well, it's if k is positive, and you divide by it, and the last line is all positive, then it's an upper bound. Upper. If k is negative, and you divide by k, and your last line alternates, negative, positive, negative, positive, negative, positive, or positive, negative, it doesn't matter how it alternates or what it starts with, but if they alternate, then you have a lower bound. Okay? Alright, and we are at homework, so we are done. Happy homeworking, and I will see you next time.